In this video, I will show you how I connect to the Dynamixel servos with Python. In order to connect to the Dynamixel servo, the first thing we need to figure out is what is the name of our serial port. So I'm on Mac here, which is kind of the same as Linux. If it's on a Windows machine, it's kind of it's one of those COM ports. On Unix and Linux, you need to look into the dev folder, and in there's a lot of TTY serial connections. The one that I have is the USB serial something. You can see I also have other stuff connected. All of these are just system serials. So I copy this, Command C, and then I'll connect to it with Python. Actually, I wrote a small Python script here. This is all of it. And the first thing that I'll just run through it. And the first thing that we do is that we import whatever we need. The first thing is serial. That is PySerial. It's the serial implementation, or the implementation of serial ports in Python. I use it down here to create a serial port. So we use serial and the serial class inside of serial. We initialize it with the name of my serial port. We set the baud rate to 57600, and we give it a timeout just in case something is wrong, so that our program doesn't hang. Then the next thing we need to do is that we need to construct a package that we want to send. So I'm doing this here, and in order to figure out how the package should look, you need to go and look at the documentation. So I have Robotis homepage open here, and the way that you find the documentation is that you click on Support, eManual, it loads, and out in the far left here, you click on Product Information. On the Product Information, you need to go to Actuators. And under Actuators, you have the different Dynamixel servos that you can have a look at how those work, and you have the two different protocols. If you update it to the newest version, you're using Protocol 2.0. So Protocol 2.0 is described here, and basically it's a matter of sending one instruction package and getting a status package in return. So the structure of the instruction package is like this. You send a header, and the header is constructed of 3 bytes. One with all ones, another one with all ones, and one with a single 0 in it. Then there's a byte that is reserved, and you can see here it cannot be FD, which is the last part of the header. That would confuse the software, because it needs to look for FFFFD. Then the packet ID is the device that you want to communicate with. I have a device connected which has the ID of 1. You can also broadcast using 254 or hex FE if you want to send to all of the servos. Okay, so we want to put in a 1 here. Then the packet length is the length of the packet after this instruction here, or after this byte. So all of this is fixed, but depending on which instruction that we give it, the amount of parameters change. So the packet length comes here for the reader to know how many bytes it needs to read. Then the instruction, which is one of these instructions, the ping to see if somebody is there, the read instruction to read from the servo, and the write instruction to write to the servo. There's other things here, but you can have a look into that. Depending on the instruction, if you want to write something, then the amount or the data that you want to write, you put in the parameters. If we are doing a ping, as you will see down here, the basic structure of a ping is that we have instruction 1 and no parameters, and then in the end, as we can see up here, there's a CRC check. The CRC check is a cyclic redundancy check, which uses a cyclic code in order to figure out if any of the bits in all of these, all of this data has been lost during transmission. That can happen if we have electromagnetic interference or stuff like this. So let's build a ping package in order to figure out if we have, sorry, I need to find the ping package. There we are. So I want to build a package like this in order to ping our first servo. Here I'm writing up the stuff that I need. The packet ID is 1, so the first servo. The packet length is 3. I can see that by seeing that after the packet length, how many bytes do we need? 3. The instruction is 1, ping. It's this one. Then I pack all of this together, first with a header. I use a byte array because it's an array of bytes, go figure. So FF, FD, that's our header up here. It's fixed, you cannot really change anything in that. Then there's the reserved word here. I set that to 0 because that's normal. Then we need to put in the packet ID and then the packet length. The packet length is divided over 2 bytes, the lowest byte and the highest byte. That is counterintuitive that you would get the lowest first and the highest. But remember, as you're sending it over the network, you're actually sending it from the beginning. So the receiver will receive first FF, FD, and so on. So it makes sense that it will receive the lowest portion first and then the highest portion. After the packet ID, the packet length, which is 3, and then 0. A byte can be up to 255, so I didn't want to make precautions for instructions that are longer than 255 bytes. After that comes our instruction. The instruction is 1, right? As we saw. Remember, I set the packet length to 3 because I need to make space for the 2 bytes of CSC check down here. Let's construct those. Looking at the manual, we'll see that this is the correct CSC for the case of packet ID 1 and all of the other stuff. But let's compute it so that you can compute CSCs for any package that you want to send. CSCs are a way to check if all of the bits have the right value. And there are several different CSC checks, and there's a CSC calculator here. It says that it uses CSC 16, that is a 16-bit CSC check, with the IBM ANSI standard. They also provide the generator polynomial, which is x16, x15, x2, and then 1. If you want to dive into it, look it up on Wikipedia or stuff like this to figure out what the generator polynomial is. The polynomial representation can also be put in hex like this, and then it's the initial value of 0. So this actually confused me a lot because the IBM and ANSI standard actually says that the initial value should be FF, or actually 4 Fs. That is all ones, but they start with an initial value of 0. So actually we have a slight difference between the standard. It's no problem, we'll just make our own CSC function. So for making the CSC function, we'll use the CSC module. So we import the CSC module up here, and then we use the function make CSC function. So we actually make a function that we can use later on. The CSC function needs to have the generator polynomial as input. Remember, or do you remember it was 8005 as this? But 8005 only accounts for these 3 terms. Actually, in order to get the first term, we need to put in a 1. This is a slight difference between different CSC implementations and so on. So the CSC mod wants all of the generator polynomial. Then we need to initialize the CSC with 0, as I was saying, that the initial value is 0 instead of FF. And then reverse false. This is also something that confused me to begin with, because actually you would read the data from the back, something like, of course, something like this, right? As it's coming in, as I said, we're reading and then we get the lowest portion first. But actually, the way that this is implemented is that we get the entire package and then we do the CSC check on it. So that's why we say we're not doing it in the reverse order. Okay, if you didn't get it, that's okay, but this is the way to create the CSC function. So the CSC function we use here, and then we take the packet. So the packet is in a byte array, but the CSC function actually wants a string. And in order to make the string, we use the bytes type. So we convert the byte array into a bytes list or a string of bytes. The CSC function then computes the CSC check here, which is actually just an integer value. So the integer value is 16 bits, but I want to append 2 bytes of 8 bits to my instruction package here. And this is kind of something strange, but what I'm doing is that I'm taking the packet, I'm extending it with a struct of 2 bytes. So capital H is an unsigned byte, and the less than indicates that I have the least significant byte first. If I took the other greater than, I would have it in the opposite order. Okay, so now I've extended that, and I'll print out the package that I'm going to send in binary and in hex so that you can see it. For now, let's comment all this out. Oh, sorry. There we go. So if we run it, nothing happened. Kind of strange. Oh, of course, I need there we go. So it's running, and down here it says all of this mumbo jumbo is simply just to join each of the characters in the packet together with colons and with a binary format or a hex format. And as you can see down here, we have a binary format, FF like this, and FD are all ones, and then a single 0 there, that's the FD. My terminal here is underlining stuff, and I don't know why it's doing that like this, so don't care about it. Then it says 0, 0, which is all zeros. Then we have a 0, 1, which is all zeros and a 1. Remember, this is binary up here. It says 03, which is the length. 03 comes here, 1 and 1. Then a 0 again. Then actually we have the instruction here, which is a 1. And then our CSC, which is not 19, but 1, 9, and 4E in hex, which is translated into this binary string. So that's the package we actually want to send over to our servo. If we just check that the check we have here actually fits with our example, and it does. 194E, right? That's the same. So that should work. So let's go ahead and write out that package onto our servo. Now, once we send this to the servo, we'll receive a status package. So I'll just scroll all the way up. We have the instruction package, and after all the explanation here, we have the basic structure of a status package. And it's kind of the same. We have a header, we have a reserved word, then the packet ID. This is the sender, not the receiver now. Then again, the package length. Instruction, which is different because we have different instructions depending on the error. That's what I wanted to say. So the instruction is 55 because it's returning it, right? But the error could be different. We could have results or CSC check error and so on, or we could have no errors. If it's 0, there's no errors. Then the parameters also is a reference to the actual instruction that we send, and then we have the CSC check. So let's go ahead and see what we actually get back from the ping that we made. So we made this ping, and we're actually going to receive this specific package. But let's see if we can go in and figure it out. So first, what we do is that we read 3 bytes from the serial port, right? That's the header. That should be the header, FF, FF, and FD. And I'll print it out down here. So each character in the header I'll format as hex, and I'll join it with a colon, and it'll say received header. So let's see if it will work. Yes. So we sent this packet, and then we received the header FF, FF, FD. Great. Now you could make some special code that if you didn't receive that header, you would receive 1 more byte to see if you would receive the header, and so on until you actually had FF, FF, FD. That could be mumbo jumbo data on the line. Sometimes there is. Okay. Then next we want to receive the body. So we receive the header. This is what I call the body: the reserved word, the packet ID, and the packet length. Because this is also fixed and this is varying, right? So I want to read up to here so that I can get the packet length and figure out how much I need to read. So I'll uncomment this. It says that the body is equal to serial port read 4. So I'm reading 1, 2, 3, 4 bytes. And I'll print it out just as I did before. And every time I'm doing this, I'm actually sending a ping package and I'm receiving a new piece of data from the servo. So I received the header. Now I received the body. 00, that's the reserved word. Then it says 1, and that's because it's the packet. Sorry, it's the packet ID. Yes, and the packet ID is of course from the servo 1. Then it says 0700, and that's because it's the packet length, right? It's 7 bytes from this point on, and that's the high one, right? So if we had more than 255 bytes, it would say something here as well. Now we are only working with shorter packages here. So 07 is actually 7 bytes that we need to read. Okay, so I'll read those bytes. Sorry, I'll go in and I'll figure out programmatically how many bytes it is that I want to read. And what I'm actually doing here, it's kind of involved, but it's not too bad. I have 2 bytes in the body, right? So the body is an array of bytes. So we index into that with square brackets, and the first, if we look here, that's the first part of the body. So that's the address 0 in the array. That's the address 1. That's the address 2 that I'm using here, and then that's the address 3 that I'm using up here. So the address 1 is actually what we want to have. So because it's bytes, which is interpreted as characters, I need to get the actual value of it, and I use the odd function to get the actual value of that byte. Then I'll actually add, and that's just for good measure, I'll add the next byte here. Now this is 0, but let's say that it was a 1 here. That would be significant, because a 1 here would mean that we had to read 255 packages. So actually, if I have a 1 here, I'll bit shift it 8 to the left, so that everything is multiplied by 255. Instead of byte shifting it 8, I could actually just write times 255. but because we're working with bytes here, in my mind it makes better sense to shift it. So those two combined is the length of the received package. Okay, and I'll print it here, bytes to receive. Let's try it out. There we are, bytes to receive 7. So in the next portion here, I'll read the parameters, and the parameters are everything after the packet length, at least what I call the parameters, is everything after the packet length and then up to the CSE. So I'll exclude the CSE from it. So parameters is equal to serial port read the length of the received package, right, that we just got up here, which was 7, minus 2, because there's 2 bytes for CSE. And I'm doing the same here. So let's see what we got. Run it. Down here it says received parameters 5500, or I call it 5500, 0128. Let's see if it makes sense. So 5500, 06, 04, 26. Something completely different, but that's because this example is made for another servo. Specifically one with a firmware of 26 or 626. In our case, the firmware version is, interestingly enough, 2.8. So 2.8, what is that? In hex, if I write 2.8 and I go to, of course in hex it's 2.8. If I look in decimal, it's 40. Remember that we updated this servo to firmware 40. Okay, so that's all good and fine, but we don't really know if we got any errors. So let's go in and get the CSE checksum, like this. So now we're receiving the last 2 bytes. By reading it from the serial port, putting it into the variable CSE sum, and then just printing it out, right? There we are. So the CSE sum that we received is 2E-C6. Again, this will not fit with this example here because we have other values inside of the package. Actually, we are checking up. The CSE check looks at all of these bytes. So if we also had an error in the header or something like this, that will be reflected in the CSE. Okay. Finally, let's go down and check with our CSU function. Oh, that's an extra line here. With our CSU function that we made all the way up here, right? How would that look with the header, the body, and the parameters that we received? Note that I'm not including the CSE sum. I'm only looking at the functional parts of the package, and I can add those together because they are strings, and the CSE function works with strings. So you can see where it was kind of awkward to use the bytes and stuff up here, it makes sense when you're receiving from a serial port. So we'll just make the CSE check here, and then unfortunately the CSE check, or unfortunately for our eyes, it's an integer that we need to pack into a couple of bytes. So we're doing this with the struct pack, just as we did before up here when we extended the package that we wanted. So this CSE check is now read out to us as the calculated CSE sum. So let's do that. There we are. So we actually received the CSE sum 2E-C6, and the one we calculated is 2E-C6. Perfect. So there's no errors, and you can go in and programmatically read each of the bytes and get the information that you want. Now, this was for the ping package, which is actually a useful package to see if your servers are online. but there's also other instructions that is more useful, which is the write to make your servo move, and the read one to figure out where your servo is. And all the information is present here in the instructions on how the protocol works. Remember, protocol 2 is used in firmware 40. You can update, or you can set a byte inside of the firmware 40 to use protocol 1. But once you took the step to the newest version, let's just use protocol 2.0. If you're interested in the control table of your servos, go to the MX series here. So I'm just looking at the MX64, and it has a control table. This is the old control table that you would see in the Robo Plus program. If you updated it, as you see here, you need to go to the MX64 2.0 version. 2.0 refers not to the protocol, but to the new control table. And here there's a lot of information about how everything works. And further, if you click on the different values here, let's click on the velocity gain, you'll see that it takes you just down the page. So up here we had the control table, and it'll take you down to the place where it needs to be. And a nice portion of this is the actual controller, that you can see how do we want to, what do we want to set, do we want to do some feed forward, and so on. Okay? So now you're ready to connect to the Dynamixel servos with Python. All in all, it's kind of the same with Arduino. You just have to make the correct serial packages and read them in the correct way. So good luck.